So let's release and drop a baseball from the roof of the Sears Towers in Chicago. The Sears Towers in Chicago is 1,450 feet high. So the ball's height, we're going to call that h, is going to be given in feet, can be described as the function of the time t since the ball was dropped. We're going to measure that time in seconds. And we are going to express the height function as negative 16t squared plus 1450. So this is h of t. Okay, so why don't we graph this function? So what we're going to do is we are going to input this function in your y1, negative 16x squared plus 1450. And if we want to look at the table corresponding to this function, we're going to do second graph, and we will be able to look at the table. I have here the first 6 values, and then in this table, it has the values between 6 and 12. Okay? Please note that at t equals 0, the corresponding y is 1450, which means that at t equals 0, the ball is 1,450 feet above the ground. Okay, at 0 seconds, that's the height of the ball. This point right here is the y-intercept of the graph corresponding to this function. Okay, so note that this number 1450, this number right here, corresponds to this number right there. Okay, now one thing that we can see by looking at the table is that after 1 second, the ball has gone down to 1,434 feet. After 2 seconds, the ball has gone down to 1,386 feet. Okay, so is this graph or is this table a representation of a linear function? Well, let's see if it is. Before looking at the graph, I can compare the rate of change. So if I look at the rate of change between t equals 0 and t equals 1, the average rate of change could be, I have to subtract the inputs, that goes in the denominator, and I subtract the outputs, and that goes in my numerator, right? And the value that I'm getting right here is negative 16, and of course is 15 feet per second. Okay, so negative 16 feet per second. With t between 1 and 2, the average rate of change, again, here will be 1 minus 0. And if I subtract 1396 minus 1484, okay, 1434 rather, the number that I get, let me just write it so you can see what I'm doing. 1386 minus 1434, and remember that this is feet and this is second, and the number that I'm going to get here is negative 48 feet per second. Okay, so this is the average rate of change between 1 and 2, and this is the average rate of change between 0 and 1. So obviously the average rate of change is different, and this graph is not going to be the representation of a linear function. Okay, so why don't we graph this function now? And what we need to do to graph this function is we need to select a window. So let's go with a minimum of x of negative 10, a maximum of 10, and the scale of 1, a minimum of negative 50 in the y, and a maximum of 1500 in the y with a scale of 1. If we go and do graph, we will obtain this graph right here. And as we look at this graph, we can see that the graph doesn't represent a linear function. It's not a line. So this graph is the graph of a parabola. So the graph of a parabola can can be opening up or can be opening down. So it's always a U-shaped figure. So this is, let me write it for you so you can see it. This is a parabola. Okay, and the parabola can open upward, and if it's open upwards, it's gonna open like that, or can open downward, downward, right? And if it opens that one, it's gonna open like that. Okay, so this number right here, as we know, because we are going to be between -10 and 10, this number is -10. This number right here is 10. This point is the point 0,1450, because we learned in previously that the y-intercept of this graph is the point 0,1450, represented by this number right here. Now, obviously, we see that this graph goes between the values of somewhat between -10 and 10. But the real domain that represents the domain of HOT is this part right here, corresponding between t equals 0 and this value. I'm going to call that value P, that represents the number or the value in which which represents the y equals 0. So this P is the x value where y is equals to 0. So the practical domain of HOT, remember that HOT is the function that gives me the height of the ball. The practical domain for HOT would be t between 0 and p, where p is the value when HOT is equals to 0. The practical range, now range corresponds to the values of HOT. And remember that HOT is the height, so the height is going to be between 0, right? And this number right here, 1450. 1450 is the highest the ball is ever going to be. So the graph of the height function, as we saw, is a parabola. And parabolas represent a quadratic function. So what is a quadratic function? A quadratic function, if we are talking about x being the input, a quadratic function on x would be the sum of three terms. It would be ax squared would be my first term, plus bx plus c. A, B, and C are going to be called the coefficients, and A, B, and C are going to have to be real numbers. And A is going to have definitely have to be a number that is not 0. If A is 0, then we have a linear function. So any function defined as y equals ax squared plus bx plus c, or also defined as f of x equals ax squared plus bx plus c, is going to be a quadratic function. So I want you to notice that we have three terms in a quadratic function, and those terms are going to have different numbers. So we have ax squared, right? And we have, let's just write it, ax squared. That's the first term, bx is the second term, and c is my second term. So first, second, and third. Ax squared is going to be called my quadratic term, right? And a is the coefficient of the quadratic term. Bx is going to be called the linear term, and B is the coefficient of the linear term. C is what I'm going to be calling my constant. Okay? Now, each one of these particular coefficient is going to have an importance in the way the graph is going to be defined, the graph of the quadratic function. So let's just talk about 3 examples of quadratic functions and see what we can see. Okay, so if we have a function such as y equals, this is my first example, y equals x squared plus 2x minus 1. We are going to have the quadratic term, and it's going to be this one right here. A is going to be 1. My linear term is going to be 2. And my constant is going to be negative 1. Okay? Remember, what we have seen is that the constant seems to be representing the y-intercept. Let's go with another example. If I have a function such as f of x equals, let's say, 3x squared, now I have that this is my a. A is equals to 3. That's the coefficient of my quadratic term, but I don't have a linear term. Or in other words, my linear term is 0, my linear coefficient is 0, and my constant is 0. Okay, now let's go with a third example. Let's say that I have y equals negative 2x squared plus 3. Now, this is my A, this is my C, and I don't seem to have a B. So, A is negative 2, B is equals to 0, and C is equals to 3. Okay, so I have two functions. One is h of t equals negative 16t squared plus 1450. In this case, A is equals to negative 16, B is equals 0, and C is equals to 1450. If you look at the graph of this function, you can see that the y-intercept is 0, 1450. So we can see that the y-intercept seems to be representing or matching the value of C. Okay? The turning point of this parabola, the turning point seems to be happening on the y-axis. Okay, we call that turning point the vertex. Okay, so the vertex of this parabola is on the y-axis. And of course, we can see that this parabola seems to be opening down. Now, I have another function right here, and this function has the same value of A and C, but has a B of 48. So for this function, A is negative 16, B is 48, and C is 1450. If you look at your calculator, you graph this function, you can see that this function, again, is having the same intercept, y-intercept, as the function we previously graphed. This function will have the y-intercept as 0, 1450. The one difference between function A and function B is that function B seems to be having the vertex is not on the y-axis, is not on y-axis. Okay? Okay, so what I would like to do is I want to make a list of the different effects that the coefficients of a quadratic function have on the graph of the function. So let's start with A. Okay? So we notice that in both cases, A is negative, and in both cases, I have a parabola opening down. So when A is negative, okay, we're always going to see that parabola opens downward. Okay? Now, when A is positive, the parabola is going to be opening upwards. Okay? Parabola opens upward. Okay? Um, so now let's go with B. When B is equals to 0, the turning point seems to be on the y-axis. When B is not 0, the turning point is not in the y-axis. So let's see if we go to B. We're going to say when B is 0, turning point. Remember that we call that turning point the vertex. The turning point is on y-axis. When B is not 0, like this example right here, turning point is not on y-axis. Okay? Now the last thing is C. What can we say about C, and what does C tell me about the graph? Well, we all know that the C value represents the y on the y-intercept. So 0C is the y-intercept in the graph. Okay, so this is the relevance of each one of those terms. Remember that a quadratic equation is always written as ax squared plus bx plus c. A tells me if the parabola opens up or down. B tells me if the turning point is on the y-axis. And C tells me where the y-intercept is. Okay, so here we have the example again of h of t equals to negative 16t squared plus 1450. So again, if we look at this function, we can see that a is negative 16. Therefore, the parabola should be open downward. B is 0, right? So that means that the turning point is on y, turning point on y. And C is equals to 1450, which means that 0, 1450 is the y-intercept. So right here we have the graph corresponding to this function, and we can see that all these things are true. The parabola opens down, the y-intercept is 0, 1450, and the turning point happens at the y-axis.